Hello, everyone. Good night to everyone that are listening to us from Turkey, and good night to everyone that are good night or good morning or good afternoon to everyone that are listening to us from different continents of the world. Today, as the first DLP of this year for IEEE PS Turkey chapter, we will be starting today with Dr. Ebrahim Vaahedi from Canada. I will have an introduction for respected Dr. Ebrahim Vaahedi, but first of all, I want to introduce the board to the listeners. Today I have my vice chair, Professor Akın Taşçıkaroğlu from Muğla Koçman University, and our chapter secretary, Professor İbrahim Şengör from İzmir Katip Çelebi University, and Burhan Egemen Özen as Turkey PS student representative. Before starting with Dr. Ebrahim Vaahedi's presentation, a brief introduction for him is that Dr. Vaahedi is an associate vice president at OATI, where he leads smart grid solution development. He has over 30 years of experience in different segments of energy industry, specializing in the development and execution of technology strategies for utility industry. Dr. Vaahedi joined OATI following his prior position with a major Canadian utility as chief technology officer, where he was accountable for developing and executing a consolidated technology plan, including the delivery of $140 million control center project. Dr. Vaahedi obtained his master and PhD degrees from Imperial College London, and he's a fellow of IEEE, and he has authored many publications, including a recent book in modern power system operation entitled Practical Power System Operation. Dr. Vaahedi has also served as an adjunct professor at the University of British Columbia for the past 20 years. As you see, we have a great colleague that will be with us, and we're honored to have him with us. And he will be presenting a topic on microgrid deployment use cases to create reliability, resiliency, and economic benefits. Dr. Vaahedi, we will be glad to listen to you, and we're leaving the show to you. We're leaving the stage to you. Thank you very much for your presentation from now on.
Thank you so much. Thank you. I'm trying to bring up my presentation. I hope you can see my presentation. Can you see my presentation?
Yes, we can see, Professor. No problem.
Professor, we can see your presentation.
I'm trying to put it on the presentation, you know.
Yes.
But for some reason, I'm having issues with it. Just give me 1 second, please.
Yeah, of course, no problem. Please take your time.
Okay.
And that's indeed a very interesting topic, and many of the people from industry and or students or from academy will be very glad to listen to it. Even in the worst case, we can see it very clearly in this version. Even in the worst case.
Okay. Okay.
Okay.
Okay. We are there.
Great.
Good morning or good evening.
The stage is yours.
Thank you so much. Thank you so much, Dr. Erdnik. Good morning, everyone, or good evening, everyone. My name is Ebrahim Vaahedi. As Dr. Erdnik introduced me, I work for Open Access Technology International. It is a pleasure for me to be giving this distinguished speech in Turkey, and it is really my pleasure. Before I start, I want to thank the executives of the local chapter in Turkey, the executives, Dr. Ednik, Dr. Akin Taski, and Dr. Senior, for all of their efforts for organizing this session. It is again my pleasure to be here. As I mentioned, I work for OATI. OATI develops smart grid solutions, and one of those solutions is a microgrid solution. And that is the topic of today's presentation. I want to talk about that. So without further ado, I am going to my next slide, which is what we are going to talk about today. The first item, I'm just going to go very briefly on what is a microgrid, some fundamental concepts, and what does a microgrid do? What are the functions of a microgrid? And then I'm going to be focusing on what is the technology framework for a microgrid to be able to do those functions. Then we will focus on use cases. What are the microgrids used for? And finally, we will wrap it up. Now, my whole presentation, I think, will take about 30 to 40 minutes, and then we have some time for question and answers. So let's start with the first one. What is a microgrid? Microgrids are defined as physical systems that have clearly defined boundaries, and they can be disconnected from the grid. So this is a grid in this case. They can be disconnected and operate seamlessly, and they can be connected to the grid. So let's look at this particular picture. You can see that we have a microgrid. It has solar generation, it has a storage generation, it has wind turbines and wind generation, electric cars connected, commercial buildings, residential buildings. It can participate in electricity markets. It can be connected to other microgrids, and so on and so forth. This is the basic definition of a microgrid. Now, let's talk about what are the drivers. Why do we use, and motivations of microgrids? The first one is reliability and resiliency. Let's talk about reliability and resiliency. There is a slight difference between the two. Resiliency is like a bouncing ball. You throw a ball and then it has to bounce back. And that is called resiliency. Something happens in your system, you want it to come back. You are disconnected from the grid, you want nothing to happen. You want to have seamless operation of your operation of your site. So that is called resiliency. Going down, coming up very seamlessly. And this is the symbol for it. Now, seamless transition between grid and islanding, and that's resiliency. Reliability deals with, power quality mitigation, available electricity during the year, not having outages, and so on and so forth. So we know that NERC and reliability agencies have defined what is reliability, how much your system has to be acceptable, not to having load not served, and so on and so forth, being able to the system being able to face different contingencies, N-1, and so on and so forth. So dealing with power quality and security issues and all of that. The second driver for microgrid is really having efficient operation. You want obviously to have the minimum cost electricity generated. And to the extent that you have your generators degraded, their performance becomes bad or worse, you want to be able to manage those. Now, the second one, as part of economic operations, sometimes you have a bunch of contracts that you have to fulfill. So let's say I'm a microgrid owner. Somebody comes to me, power producing agreements. So they come to me and say, I supply your solar and battery generation, but but I want you to use them so much during the year. And so I have a contract to fulfill. Now, in this case, the microgrid has to also fulfill that contract. Or you may have a net metering agreement with a utility. So that agreement says that during the year, you have to be, you know, supplying or importing electricity within this threshold. So you have to, let's say, sell me this much, and you have to be buying from me this much, so that we have this contract. So your microgrid has to be able to to manage to that contract, to comply with those contracts. So if you have a number of contracts, this is another issue with microgrids, that you have to be able to comply to those. The third item is environmental stewardship. So obviously you want to make sure that the electricity that you produce, you have the minimum footprint. And this one is always a balance between environment and economic operation and efficient operation. How much you want to reduce your cost versus how much you want to benefit environment. Finally, a microgrid can be connected to the electricity market and sell electricity, or it can provide grid services to utilities. Now, what is grid services? Grid services are some electricity products that ensure reliable operation of utilities. So things like regulating service, things like fast frequency, things like capacity reduction, capacity build. Those are some grid services that utilities can produce themselves, but they can also choose to purchase it from other people, other places, like microgrids. So these are different drivers for microgrids. And in this particular case, you are creating reliability for the utility, and meanwhile you are both enjoying some economic benefits. So now let's move to what is a micro. I'm sorry. So this now, what I want to do now is to tell you that these microgrids have created a paradigm shift. And let me tell you, give you an example here. So what do I mean? Historically, we have had a grid operation creating, we have systems which create generation, remote places. We have conventional generation located in remote places, and they are transmitted using long transmission lines to the urban areas, and getting transmitted through distribution systems to local loads. Now, this has been historically, this is what has been happening. And in this situation, you can see that we have grid is the main supply of electricity. We have some of these consumers, or residential, commercial buildings. Some of those have had self-supply resources for emergencies, like diesel generators. And the problem with this solution is that as time goes on, you have degraded reliability. All of these assets become old, and your resiliency comes down. You can lose electricity because these systems go out. And as load increase, the transmission and distribution need to be upgraded. They get congested, and they need to be upgraded. Now let's turn. Now again, I'm going back to the previous picture. So before I complete that, now, to see the problem with this particular situation, the local utility, the place I live, the city I live in, is Vancouver, Canada. Now, in this particular place, you see that um, based on this link that I have included for you, the local utility is spending $2 billion annually on infrastructure maintenance and upgrade. So they have this system and they have to spend $2 billion annually to ensure that they maintain these systems, the transmission and distribution systems, and uh, and and which is a huge investment for them. If you go to this link, it shows their investment budget and investment capital budget that they have for the next 10 years, and every year they spend $2 billion on this. Now let's reverse that. What will happen now with a system which has microgrid? Now in this particular case, what you have is that this time we do not rely on remote generation, long transmission systems. In this particular case, you have a microgrid that it will self-supply, it will self-generate. It uses grid for emergencies and for other purposes. It minimizes transmission and distribution upgrade. You don't need now transmission and distribution upgrade because these are self-supplying. It will enhance reliability, it will enhance resiliency, and it will enhance efficiency. Now, let's look at this. Before, in the slide before, electricity was coming from, top down. And we needed all of that infrastructure, upgrade, investment, and all of that. Now, this time, we are going to be self-supplying in here. We are minimizing the use of distribution and transmission systems. Therefore, we don't have those. And this is really turned around the paradigm for generating and consuming electricity. Now what I want to do is I want to focus on what is a microgrid. Microgrids come in different shapes and sizes, and this slide is an extremely important slide. People think that microgrids are just a couple of resources and a load, and because of the name microgrid. I have come across microgrids that they start from a couple of kilowatts and they go all the way to many thousand megawatts. So you have a huge range. Now, let me explain something. Now, this is the one-line diagram or logical diagram of a microgrid. So let's start from the left. You can see that I have broken this down into 3 separate segments. The first segment is the electrical system. The second segment is the cooling system. And the last one is the thermal system. Let's look at this. The electrical system, we start with a diesel generator. You could have a diesel generator that consuming fuel. You can have a PV generation. You can have wind generation. You can have electric storage. You can have a connection to the utility, and you can have a second connection to a different utility or the same utility. You can have a micro turbine, which is consuming gas. You can have a critical load in the bottom. You can have a dispatchable load. Dispatchable load are the loads that you can do without for some time. And then you can have an electric chiller for chilling, for chilling consumption that you need. Now, this was my electric portion or for my electric segment. Now, if you have a micro turbine, you can also have the option of having a combined heat and power system. If you were to have that, the exhaust from the micro turbine can be used in the absorption chiller and heat exchanger to create cooling as well as heating. Now, let's go to the cooling part of microgrid. The microgrid can have some cooling requirement. Now, where is that going to get the cooling requirement? You could have an electric chiller that we just discussed, or additionally or optionally, you could also have an absorption chiller that uses exhaust from the microturbine, and it can create cooling. Now, also in some districts, they have cooling, so they sell cooling. So you could be in a district that you can buy your cooling from outside. They deliver to you through some system the cooling. They have pipes that they provide you with cooling. Or and also you can also have chilling storage, similar to having electrical storage. You can have chilling or cooling storage, and this is your chilling load. Now you can supply your chilling load from the electric chiller, or you have other options that I have shown them in this particular segment. Now similarly, for the thermal system, you can use a gas boiler to provide your heating requirements, or you can use again the exhaust from the microturbine through the CHP heat exchanger, and that can create for you the heating that you need. You can buy your heating from the district heating if that is available. You can have a heating storage, and you can have heating load. Now, why am I showing this? A microgrid could be only a PV, wind, and a load. A micro turbine could be all of these. Now, and that is why I'm saying a microgrid can have, it could be very complex and complicated in operation, or it could be simple. Now, let's look at the complex ones, and let's see what is involved in the operation of this. So now let's say you have this system, the complex one that I showed. Now, if you want to optimize your operation, and let's say that you find that the gas price is high, you cannot just say, I am not going to be using my micro turbine, because this gas generation, micro turbine generation, is coupled with the chilling, uh, absorption chiller, and heat exchanger. And yes, the price of electricity could be high, but it is also producing chilling effect and heating for you. So these different segments have to be all coupled and collaborated and coordinated and optimized together. It is pretty complex. It is very complicated. What you are doing is you are creating some generation in the microturbine, but that generation, it is not electricity. It is heating, it is cooling, and you have to take all of that into account when you are dispatching that, when you are making sure that the microgrid is operationally optimized. So again, the reason I'm showing this is to bring to your attention that microgrids are, they could be very complex, and or they could be very simple. Okay, now in a few slides before, I mentioned what are the drivers for a microgrid. We wanted them to be reliable and resilient. We wanted to have operational efficiency. We wanted to make sure that we have least environmental footprint, or environmentally responsible. And finally, we wanted to sell grid services, and we wanted to sell electricity in an electricity market, uh, to provide additional revenue. Now, in order for us to make sure that we can do all of that, there are, we need to have a technology framework. Technology framework means that at the lowest level, you have your physical systems and your assets, your PV, your wind generation, your diesel generator, and so on and so forth. At level 1, you have your protection system and switchgear. Now, the solution for a microgrid starts from here, microgrid management system. At the lowest level, you have an automation control. that automation control looks after islanding, resiliency, make sure that you have, seamless islanding. If something happened, you go to island and your system continues to operate. And then you come back to the grid and get grid connected seamlessly again. That's called automation control. Now, the second level is called system operation management. That really ensures that you are operating efficiently, you are using the least cost, or you are environmentally, very responsible. Whatever your objectives are, that is the second level. That's running the system very efficiently. The third one is really external interactions for electricity markets and interactions with, utilities, making sure that you have all of those to sell electricity and other, you can participate in markets, you can sell electricity and grid services to utilities and other programs, the other utility programs. Now, this diagram shows the same diagram using the OATI, microgrid management solution, which is called OATI GridMind. You can see that at the lowest level, we have all of these physical systems. We have switchgear and, level 1. The automation control, again, as I mentioned, is islanding and grid transition, voltage control during islanding, frequency during islanding. And then this, the base, what I call GridMind base, or the middle one in green, it is really making sure that you run your system very efficiently, making sure that you have uh, you know situational awareness, and this is the operator connected to this, and he wants to look forward to make sure that it has situational awareness and it is running its system in the most efficient way. Level 4 is really what I mentioned, that now you want to participate in different programs. You want to make sure that you have optimization, environment, and grid participation in utilities and electricity markets. We have another module which is doing that, and we have taken it to level 4. Now, it is important to see that when a utility has a microgrid, they can remotely, or any, depending on the role of different people that they may have, they can be a remote operator of the microgrid, or you can have an on-site operator of the microgrid. It is all connected to the system through the cloud. Now, this was the first part of my presentation. And basically what I was trying to do was to look at, what is a microgrid? What are the functions of microgrid? What are the drivers of the microgrid? And what is the technology that you have to have? This is called the microgrid management system. You need this technology to be able to fulfill the requirements of a microgrid. Now, there are plenty of use cases for a microgrid. I'm going to focus on 5 different use cases, but this section is really for thought-provoking. I want to speak to that so that you can think about other use cases. So I'll talk about community microgrid, critical facility microgrids, remote community microgrids, microgrid participating in electricity markets, substation microgrid, and microgrids providing grid services. Let me go back again. So microgrids providing grid services. For all of these, we have some examples, and I'm going to point out the examples so that they are really happening in the field. And as much as possible, I give you, the link for a project which is doing these things. It is in these areas. So let's start with a community microgrid. What is a community microgrid? A community microgrid, normally, like as this picture shows, they have a number of residences, It could have community solar generation. It could have community battery. It could have a community swimming pool. And also it could have, each residences may have, the roof solar generation. So this is what the community microgrid is, and it is connected to a utility. And what happens in this case is that the system wants to be able to manage its operation. It wants to be able to withstand disconnection from the utility. It wants to be able to participate in the utility program to reduce its electricity when they have a peak load or something. And an example of this particular, microgrid is a microgrid that OATI has been building in North Carolina. It's called NCEMC Eagle Chase Microgrid. You can Google that, you can go to that. And this is exactly, as I mentioned here, this is providing a microgrid for a community. Now, as you can see, the microgrid controller in this case does all sorts of different functionalities. And again, the resiliency is one of them. Resiliency, making sure that the system, after something happens, disconnects seamlessly from the utility. The next one is critical mission. Now, what is a critical mission? This picture is a control center, and this one is an airport. This is a critical mission microgrid, or mission critical systems require a very high degree of resiliency and reliability. Right now, the present solution is that you use a standby generator with limited sustainability. So if you look at your control centers, you will see that they only have electricity or diesel for 2 weeks. They will have diesels for 2 weeks. So if something were to happen, they have to rely on diesel generation. And but whereas if you become a microgrid, then what you can do is that you can manage islanding restoration, you can generate, you can operate efficiency, you can participate in utility programs. And again, examples, as I mentioned, control centers, data centers, airports, and hospitals. And the example for this is OATI Microgrid Technology Center. What we have done is that we have OATI, OATI, create software and utilities subscribe to that. Right now, there are 2,300 utilities in North America which use OATI software. OATI has a data center. It has 2 data centers, and one of the buildings is built using a microgrid solution. If you look at this particular one, you can see that it has wind turbine, solar generation, a storage, micro turbine, diesel generator. It is used as a data center and office space, and other things that it has. It has absorption chiller, electric chiller, boiler, a storage tank, air handler, heat exchanger. So it is quite complicated. And the real life picture of this system is this one. The facade of the building changes. And for example, for the Pi Day, it looked like that. For the St. Patrick Day, it looked like that. But this is that building. They have built this building using a microgrid solution. And it is very resilient. It has two feeds from the utility. And it obviously they are using the master controller or the microgrid controller that was designed and developed at OATI. Now I want to talk about another application or use case, and that is called remote systems. Remote systems are the systems that they are located in a remote location for anywhere. It could be in Turkey, it could be in Canada, it could be in the US. And they have no grid connection, or they have very limited grid connection, only a radial line. So let me start again. So again, so they have very limited connection to the grid or no connection. So uh, some face harsh winters with transportation issues. So if if they for some if they are disconnected from the grid, some of these systems go down for many days because the system cannot sustain itself. So they go down and they will be down for many, many days. So the example for this is remote communities in Canada and the USA. And these systems, one of the things that can be done is that you can turn these into microgrids and create flexibility, just making sure that you select some of your loads to become dispatchable. So you create flexibility, and then you manage system operation. If you are disconnected from the grid, you can manage your system operation for a long period by just supplying maybe the critical load and making your system very flexible and managing islanding, prolonging available resources and restore the system when the grid is back. Right now the situation is that if such a system goes down, for some reason is disconnected from the grid because it is very inflexible, all of a sudden the whole thing collapses and it will stay out for many days. And sometimes it is very difficult. They have to send diesel by air, ship diesel by air to those communities. And this is called remote community. I'm sure there are remote communities in every country. Um, Another one is connecting the microgrids to electricity markets. Recently, there was a FERC, a Federal Energy Regulatory Agency in the US, came up with an order, and it said that everybody who has a DER, distributed energy resource, even if it is from 1 kilowatt to 10,000 kilowatt, they can connect it to electricity market and compete on a level playing field with organized capacity energy and ancillary services and markets which are run in the US. So I'm sorry. So what microgrid controllers can do in this case, if you have microgrids, they can provide electricity to provide electricity market transaction solution. They can provide that transaction solution so that the microgrid can participate in the electricity market. Again, for this system could be a community micro grid or anything else, but it can manage the normal operation of the microgrid, and then it can participate in the electricity market. This work order allows any distributed energy resource, including a microgrid, to participate in the market. Now, another application is distribution substation. This is the picture of a distribution substation. Conventional distribution substations are fed from bulk electricity. Any issue in one area will propagate to all systems. And this is the problem, that if you have an issue with one of your major transmission lines, all of your system will collapse. Now, distribution substation microgrid make a substation self-sufficient. So what we are doing is that we are making a microgrid out of this distribution system. We are going to make this distribution system self-sufficient. You have a diesel engine, you have battery, you have solar generation. You can have a microgrid controller and turn this into a microgrid. And distribution microgrid make the substation self-sufficient, and the microgrid controller makes sure that you are running the system very efficiently. If you are disconnected from the grid, something happened to your grid, you can withstand that, you can eventually connect yourself to the grid and optimize your resources, your operation. Um, so an example of this is that, California substation microgrid. So let me explain this. In California, in the summers, it is very hot and it is very sunny. If there are winds or something, what will happen is that some of the lines could, you know, just be disconnected, or just dangle, and then, and what happens is that um, they touch trees, and they could create a lot of fire. So what they are doing is that they are now disconnecting, they are trying to disconnect the major substations from the transmission system. And this picture shows that California will be relying proactively, trying to, a few years ago, they had major fires, and California will rely um, on proactive power outages. So what they are trying to do, they are trying to create microgrids so that they are not relying on their transmission system that could create fire. Now, this could also apply to other situations. So let's say, a few years ago, I was in a country that they were saying that one of our problems that we have is that when something happens to our transmission system, we lose everything. Something happens in our transmission system. Either a transformer substation goes out, there is some accident somewhere, there is something happens, an airplane comes down, or something happens to the system, all of the system has to go out. So with this situation, so you are minimizing the impact of the system. You are breaking the system into different parts, and this is called distribution substation microgrids. um, I think this is either my last application or one to the last. Um, what is microgrid with grid services? Um, so um, let me first of all define what is an aggregator. Aggregators in the US are entities that aggregate residential and commercial assets to offer grid services to the utilities. So let's pause on that. So there are some people, some entities, they come forward, they say, okay, I go and register different residential and commercial buildings, and I can provide you grid services. Now, what is the benefit to the utility? The utility has to set aside a huge generating station to provide these grid services. They have to invest in a huge, you know, generating station to generate these grid services. So they buy it from the aggregator. And what happens in this particular case is that you can have, grid mines, you can have microgrids participating in this. So let's say in this situation, and this is of course an example of OATI, becoming an aggregator, and so what in this case, what happens is that you can have residential, commercial communities, and in this particular case, you have a commercial building that it is participating, and it is being controlled, it is managed as a microgrid, and it is participating in providing to this aggregator grid services that in turn it aggregates them and provides it to the utility. Now, one example of this is that um, we have a project. OATI has a project in Hawaii that it is acting as an aggregator, and it is aggregating, um, you know, single and multifamily residential buildings. It is going around and registering through sub-suppliers. It is they are coming, they are aggregating single and multifamily residential buildings. We have, again, through another supplier, we are getting university campuses that they're becoming microgrids, and they are participating. And there is also individual residential buildings that they have battery and solar generation that they are also participating. So we have suppliers that they are bringing these and they are aggregating these, and then we are also aggregating microgrids in this system to provide to Hawaiian Electric and Maui Electric system, the utilities. We are we are aggregating, and we are providing it to those systems. So in this particular case, I'm focusing again on the microgrids. We have developed microgrids out of each of the university sites are microgrids, and then they can also provide grid services to this utility. Again, the benefit for this utility is that they do not have to invest on a huge generating a station and provide grid services. They can purchase and procure that from aggregators. Okay, I think I have reached the end of my presentation. I just want, with a few words, to wrap up what I said. I said that microgrids introduce a new paradigm. Previously, we were. I'm sorry, there is a typo here. Electricity was being generated vertically. Now microgrids are turning that. They are generating the whole thing down there, and we are saving on the upgrades and maintenance of the transmission and distribution systems. Microgrids come in different sizes and shapes, reinforcing different drivers. And microgrids, it's not just a simple little microgrid. You can have a 2,000 megawatt microgrid, and they could be very simple, they could be very complicated. You need a technology framework to enable different requirements. To be able to fulfill different requirements, you need a proper technology framework of how you are going to do that. There are many use cases. Just for thought-provoking, I wanted to be thought-provoking. I provided a few examples, but there are more. I'm sure you can think of other use cases for a microgrid. And finally, we need a sophisticated microgrid controller to be able to in the deployment of the microgrid and fulfilling all of the drivers that microgrids have. And that is really the end of my presentation. I will be happy to answer any questions that you may have. Thank you.
Thank you very much, Dr. Ebrahim Vaahedi. It was actually a very nice presentation. It's a hot topic to provide microgrids in electric power system operation, and there are very different use cases, as you already mentioned. And I think all this content was very satisfactory for all the audience, and we actually had a peak of over 130 participants at the peak. And I think that we have I will get the final numbers from the student representative, but I think that we will have independent considering independent number of persons, we have something like over 200 people that attended this course till now. So wow, that's good audience, actually. Thank you very much. And it's a very nice topic. And let's go for the QA session. Actually, I'm leaving the board for Akın and Ebrahim for this. Akın, could you start for this? And again, will help us for directing the questions.
Thank you, Ozan. Professor, thank you very much for this nice presentation.
My pleasure.
I would like to start with the first question. Also, I think you can see it on the screen. Most of I think it's virtual power plant and microgrid related companies focus on energy management, optimization, transaction technologies, and provide software-related solutions generally. Do you think infrastructure layer is still a gap?
Yes, I think microgrids have to be have a complete infrastructure. You can't just say let's have operation or VPP or something for economic purposes. You need to have a complete solution. The most important solution, though, is resiliency and reliability. You have to have resiliency and reliability for many different cases. So from a community microgrid to remote community to critical buildings, any situation that you think of, you really need resiliency and reliability.
Thank you. Ebrahim, do you want to read? Yes.
Okay. Yeah, the next question from our chapter chair. Maybe he might want to ask the question.
Yes, you can ask.
I can also read.
Oh, you can ask, Ibrahim. It's a combined question, actually. I have a second one also in the same question, just below this. Maybe after reading this, Egemen can also ask the second one, and I can get a combined answer from Dr. Vaahedi.
Okay, let me read it. Considering the distribution system substation microgrid example in California, how can IOCOs in different locations benefit from providing microgrids to alleviate the high impacts of unexpected events?
Yeah, I think that is a very good question. I think what happens is, unfortunately, we have built our system all in a contiguous and uniform way, and they are not designed to absorb different accidents and impacts, environmental impacts. I think if ISOs, the system operators, everybody, they will be really relieved to see that if something happens in a part of their systems, they can they can just put an elastic band around that and just said, okay, the impact of this is localized and I focus on the rest of the system. And I think this particular question, in one of my visits to a control center by the people, brought up to me that we have a system, a whole system is not reliable. And when we lose one transmission, the whole system goes down. What can we do? And everything can happen in the summer, in the winter, accidents. So I am, the system operators will hugely benefit from this. And California has started that.
Okay. And I think this is the second part of the question. If we take the recent Texas example into account, what should be the starting point for providing possible microgrids within the distribution system structure?
Yeah, so first of all, obviously there is cost involved in microgrids. Nothing comes free. You have to, if you want, let's say, go back to the previous question. If we want to look at that, there is cost. There is cost for installation of the PV batteries. There is cost to make sure that you have all the control systems, but there is also regulatory burdens. The regulatory burdens are huge. If you want to build microgrids, there is always government agencies and regulatory issues that they are there. So these have to be streamlined. You have to make sure that there is always source of funds that you need, but cost benefit analysis can be used for those. But at the same time, you also have regulatory impediments, and those have to be taken care of. And they are not easy.
Professor, the next question is, an advanced communication infrastructure has to be provided in an adaptive microgrid scheme for ensuring information flow between local loads and system operators. I think this is the first statement on the screen. Probably you can't see, but the second one, the main part of the question. However, communication network can also be affected by the extreme event. How could the system operators deal with this type of challenges when integrating microgrids as a resiliency resource?
Very good, very good question. I think this gentleman is focusing on the communication infrastructure. Many microgrids, or I'm sorry, this lady, many microgrids use local communication systems like fiber, or these different systems, Ethernet, to connect to different assets. But if you are far away, you have to think about two things: communication system and security, and both of them are difficult. So you can have different communication solutions, but sometimes security can become a problem. And now you have to think about, you know, communication experts are going to come in. Now, whether I should be using Cell or whether I should be using LoRa system, LoRa system has, you can have LoRa, which is free, low frequency communication system. It is almost free, except that the reach is, you have limited reach. And so anyways, you can have, the communication experts need to come to this. And then the other problem, as I mentioned, there are some solutions for security. So for example, OATI has a, has a solution which is called grid control. And grid control is a device that they put it in the field, and it will kind of gets signals, but it becomes, now from that point, becomes safe until it's sent to the cloud. So with that solution or other solution, you can use a VPN or something. So that on its own, the communication system is a completely different field. I think the experts there, I'm sure they can deal with making sure that they have communication, long communication systems, as well as making sure that the system is secure. That is a challenge, by all means. I'm not an expert in communication.
Okay, the next one. Which electricity markets can microgrids participate in? How does microgrid operator manage energy imbalances, positive or negative, in real time?
Okay, so first of all of the electricity markets that, whether they are in the US or in Canada, for example, we have in Alberta, we have in Ontario in Canada, and in the US there is California ISO, it was mentioned, PJM, and the major New York ISO, and so on and so forth. Anywhere that you have an electricity market, these can participate in those. Now, how does a microgrid operator manage energy imbalance, positive or negative? So now what happens is that the microgrid is normally connected to the grid, and it has a contract with the grid. Now what it can do is that what they normally do is that they go during the night and so on. They can, when there is off-peak times, they can get electricity, they can fill up the storage and all of that. During the peak time, they can sell back. So if with when you say how would they manage energy imbalance, that is the way that the microgrid, depending on what, of course, the other contracts they may have. They may have a power producing agreement, they may have a net metering agreement. They have to see what contract that they have, and within those tariffs and contract, they have to respond properly.
Okay, thank you.
You're welcome.
Professor, the next question is, what are the key enablers and accelerator of microgrid utilization and commercialization?
Yeah, so that is again a very good question. I think if to me, some of the simplest solutions is, let's say, if you look, let's say, in Turkey, and look at the areas that they are not getting electricity. In the example I was showing is happening in Ontario. The remote communities, they are very far, and when something happens to their distribution line, the system will be down by many days. And they have, let's say, a diesel generator. They have to bring up the diesel generator, but the diesel has to be shipped to them by air, because it is very cold and so on. So now let's look at one remote community in Turkey. So let's say if you have a remote community, what will happen if something happens to the connection that they have? If they don't have connection, How do they supply electricity? How do they do that? Do they use a diesel generation, which is environmentally not good? Do they have, how do they get diesel generation? So if we focus on very simple solutions and try to come up with a simple microgrid, I think it starts there. You have huge, huge enablers that way. For example, there was another case. There was a control center that was being built in Ontario recently, and they talked to us. We discussed with them. We said, do you want to have just diesel generators, or do you want to make your control center a more active control center? Generate and then sell, buy. Don't sit down, don't be passive waiting for something to happen to you. Become passive, become active. So you have to look at the use cases, and those are really the enablers and accelerators, and see which one is going to create benefit for your for in that region.
Thank you.
You're welcome.
The next question is about another hot topic for today. What do you think about the importance of peer-to-peer energy trading to other microgrids in the case of grid outages?
Yeah, that is also a very good question. What happens is that's an application that I didn't mention. So there are some community microgrids that they say, if we go down, we can supply not only our own load, but we can also supply electricity in the neighborhood. If there is a fire station, we can. It's a critical service. We can provide them electricity. If there are other, and I think this gentleman is also talking about peer-to-peer energy trading to other microgrids or other critical systems, and I think that is another application that has been talked about.
Thank you. It's good to see that we still have the questions. The next one is actually is a specific question, but if you have any idea, what do you think about potential role of blockchain technology in microgrid management? You know, this is a hot topic.
Yeah, I've heard about blockchain, and I have seen it presented. It is an upcoming, technology from Coinbit and all of that. To be honest with you, I don't know how that can improve the controls and maybe peer-to-peer, because it was mentioned in the previous question, peer-to-peer. This blockchain can maybe applied into peer-to-peer. Obviously it is part of the microgrid controller. We need a good microgrid controller. Blockchain could be a potential, but I'm not an expert in blockchain. Unfortunately, I can't talk about it more than I really should. But I'm sorry about that. But that is how much I know about blockchain.
No problem. Thank you. Of course, as I said, this is a specific question about the blockchain technology.
Yes. Thank you.
The next question. Dear Dr. Vaahedi, here is my question. That is, is there any legal restriction about the total installed power of microgrids? I mean, how much the total power makes it as microgrid? Thank you.
Yeah, so that is another good question. I think utilities, they are facing a situation that they are losing their customers, and some of them have become more active in the US, so that they are also creating their own microgrids, like California. So the utility says, okay, I'm making this part a microgrid. So if there are investors, there are no limit to the microgrids. There are regulatory impediments, but I think there are no limits to the amount of microgrids you can have. But obviously, utilities are facing a major challenge right now because they are losing their customers, and I think that is something which is happening in the market right now. But to answer your questions, there are no limits to creating microgrids.
Okay.
Thank you. And the last question is, In what way the machine learning could be used for management of energy of microgrid? And could you please give some examples?
Yes, so this is also a very good question. Um, we are also involved in machine learning, and we are using machine learning for forecasting. And as you can, as you know, I didn't explain it in my presentation. When you want to control the microgrid controller, when you are setting set points for the resources and forecasting for situational awareness, scheduling for the future, what you need is forecast of the load. What you need is the forecast of the DER. And then from those, and then you from your generation, your DER generation forecast, your load forecast, you know what resources you have to use. And right now, a lot of work is going into using machine learning to coming up with those solar forecast and DER forecast and all of that. And that is being used as part of the microgrid solution. Now, if you have other ideas about the microgrid controller to become using machine learning, obviously that is another avenue for research. But unfortunately, I haven't been involved in that particular area.
And if you don't mind, let me ask the last of the last by me. I think we have another additional one, but just to clarify a question that was asked before. I think it was Alper that Professor Alper that asked the question. Whatever he meant was, what is the power rating of a microgrid? Below 1 kVA, below 1 MVA, below 1 GVA. What's the level of a microgrid?
Somebody told me one of the microgrid providers told me they have developed a microgrid in a country for a oil refinery in the Middle East. The amount of that is bigger than 2,000 megawatts.
Oh,
2,000 megawatts.
So this is still a microgrid.
That's a microgrid. Because it is a refinery, it is creating electricity, it is doing all of the work, and it has to remain on its own.
It has a great connection.
It has, and it has to be controlled. It has to have frequency control. If it is disconnected from the grid, it have to have voltage control, frequency control, going very smoothly, going to island, coming back to the grid. So you can have, there is no limit to that. The rating, there is no limit to that. And then when you start small, one of the communities that we worked on, the microgrid we built, has 30 houses, which are like something like 100 kilowatt. But it has
still a microgrid.
But it has some community load and other things. So the total, I think, is about 300 kilowatts. But it can be very small and it can be very large. So, and I think the slide I had, that they come in all sizes and shapes and different complexities. And I think that was for that purpose.
That's exactly like this. And last question is actually a float, but let me start by reading it. Before the start, sir, in OATI Microgrid Technology Center, you mentioned about a small wind resource. Actually, I'm designing a microgrid which includes a wind turbine, and I faced with the distance challenge for wind turbines. My question is, what do you mean with small wind? So we know that the distance between resource and load can be a problem, and below it continues still. So do you mean that small scale wind turbines can be assembled close to our other loads in a local area? Is there an example of it?
Yeah, so this one was really it is just one wind turbine on top of the building. That building that I showed, which, it also has that particular one to make sure that this system can manage in the future other wind turbines which are further distanced from the building or connected to the building. But this one was also installed. I don't think it is big. I think it's about 20 kilowatts, but it was installed to demonstrate that the whole solution is being developed to manage different types of resources.
That's fine. And I think we have no more, but there
Okay.
are still thanks and there are still hellos and other things. So that, Dr. Vaahedi, thank you very much. We kept you a lot longer than 1 hour. We were expecting below 1 hour, but we kept. There is a great traction from the audience. So that, thank you very much for sharing your great experience in the field. And I'm sure that the participants have gathered a lot from your presentation. Many thanks also my vice chair and my secretary, and also again as our student representative. And now we are ending the live show, and we hope to see all of you in the next DLP lecture that will be exactly tomorrow at these hours. So that we hope to see you very soon again with this great audience, great number of people. So thank you very much for attending our live show. We won't let you go, Professor Vaahedi. After the live show, let's meet you.
Thank you so much. Again, I want to thank the executives of the chapter for inviting me and scheduling and organizing this session. Thank you so much. Bye-bye.
Thank you.
Thank you.
Thank you. Bye-bye.
Thank you very much.